Alright guys, we're going to go over an example from your text based off of the discussion in the prior video we had on vertical tension. So we're going to look at page 106 and complete example 4 of a vertical type tension problem. Alright, so in this problem it says a 50 kilogram bucket is being lifted by a rope. The rope will not break if the tension is 525 newtons or less. The bucket started at rest after being lifted 3 meters. It's moving at 3 meters per second. If the acceleration is constant, is the rope in danger of breaking? Alright, so let's start with the free body diagram. We're lifting a bucket. There's my bucket. The bucket has a weight this way, and we're lifting it with a rope, so it has a tension this way. Now there's a few things to be careful about at this problem, but let's fill in other things we know. Off to the side, some other givens. The mass is equal to 50 kilograms. It says the rope will not break if the tension is 525 or less. Now here's where we got to be careful. In a problem where we decide if the rope breaks or not, we're always going to be given a max tension. But we got to be very careful. In this exact kind of problem, oops, I meant to put 525 there. In this kind of problem, we don't actually use that 525 as the tension. This is just what the max is. What we need to do, our goal is to find the tension based on the acceleration, which we also need to find, you'll see here in a second. We need to find what the actual tension is and compare it to the max. And if the actual tension is bigger than 525, it breaks. If it's smaller, it's good. What we don't want to do in a if it will break or won't it break kind of problem is use the max tension in solving. We don't. We find it and compare it to this number. So it's an important number, we just don't use it in the solving until we determine if it breaks or not with that number. It also said the bucket starts at rest. We got some old stuff going on here. Starting at rest, if we recall, is VI equals 0. It's going to be lifted a D of 3 meters. And it's moving at 3 meters per second once it goes through these 3 meters, so that's the final velocity it reaches during this distance pulled. Now, we haven't had a problem yet, at least not in this chapter, a force problem that didn't straight up give me the acceleration. We need to find it using kinematic equations. So remember, as I said earlier this year, you never know when old stuff comes back into a new problem. So we can never forget old things, old equations, okay? And if we don't already realize we need to find acceleration, you will when you start setting up this problem. Really, the first thing we end up doing is saying that Newton's second law, F net on the y-axis, is equal to m times the acceleration on the y-axis. That F net is the total of the two forces, the up one minus the down one, the tension minus the weight, and that equals m times ay. Remember, our goal is to find tension, get it by itself, so we would do that by adding weight to the other side. And might as well do one other step here. Remember, weight, F sub g, is also mg. We could sub that in. So we're ready to find tension, but if we haven't realized it yet, we got a problem. We know mass. We know little g is always 9.8. But at this point, we're like, oh, wait, to find tension, we need to know this acceleration. They didn't straight up give it to us, but it gave us stuff that we could use the kinematic equations to find A with. And that's old stuff, so we're going to have to do a little sidestep here. All right? So before we come back up to this equation, if I need to use this to find A, we got to find the right kinematic equation, the one that has VI, D, VF, and A. And that would be kinematic equation number 3. If we use our old list of them, that would be VF squared equals VI squared plus 2 times AD, and VI is 0, so we could get rid of that. Solving this for A, we divide over 2D to the other side with VF squared on it. Plug in the numbers, we would take 3 squared divided by 2 times 3. And that will give me 9/6, which is exactly 1.5 meters per second squared is my y-axis acceleration that I'm yanking up on this thing with. Now we use that. So let's go back to my originally determined formula and just bring it down here, okay, and plug into it. And get this all on one screen. So now that we have that acceleration, we could find this. The tension is equal to the mass of this bucket, 50 kilograms, multiplied by this acceleration we found through the old methods, plus 50 times 9.8. Remember, 15 times 9.8 is the regular old real weight of the bucket. So if the bucket were just hanging still vertically or being held vertically by the rope tension would be just that. But because we're yanking up on it, we're inducing an apparent weight on it that makes it feel heavier to the rope, so it'll have a higher tension. So we calculate this out. And we get out 565 newtons if I'm yanking it up with an acceleration of positive 1.5 meters per second. And now here's where that max tension comes in. I compare it. That number that we saw for the actual tension, 565, is less than the maximum listed tension of 585. So this thing should be good. It doesn't break. All right. Now if we yank it a little harder, maybe that causes a greater acceleration, and maybe that causes up to get over 585. But in these conditions, we're good. So that's one typical type of problem that you may have for tension. Now, there's not another example, but I'm going to explain something. There's a variation of this problem. Okay? There's a variation, which you will run into soon, of not being asked whether it would break or not, but asking to find the maximum tension if given the max acceleration or vice versa. In that case, let's take the scenario. Oh, excuse me one second. Actually, I lost contact here with my screen. So I will repost a second part of this video once I get it fixed.